Hi, this is Amy Seipke, Color Materials Librarian here at the College for Creative Studies. This presentation today will be on polymers, an introduction to what they are and what they can do. So let's start out with a design scenario. Say that your employer wants you to design an outdoor individual party dining pod. You could make that out of wood or metal or some living climbing plant. But what they want is for it to be easy to move, lightweight, quick to build, and most importantly to them, inexpensive. What material would you choose? If you were to come to me for advice on this project, I would likely recommend looking into what type of polymer you could use. Polymers can be lightweight. They can also be preformed into the shape that you need them to be so that it makes installation easy. They don't require additional treatments like paint or stain once they're installed, making it quicker to install and have it ready for use. They can also be weather resistant, taking wind, rain, snow, anything Michigan weather can throw at them. And most importantly to your employer, they can often be inexpensive. So what is a polymer? The word polymer comes from two different Greek words, poly meaning many, and mer meaning a part. So a polymer is any material that is made up of large molecules consisting of many repeated parts. A polymer has a long chain molecule that looks like this, made up of separate monomers. As you can see, the pattern just repeats itself over and over and over. On this screen, you can see a specific polymer. This is polyethylene. It's made up of repeating ethylene molecules, joined over and over to form a long chain. As you can see within these brackets, this is the monomer ethylene, and it's just that repeating pattern over and over in a large chain. While many people use them interchangeably, polymer isn't really just a fancy word for plastic. Plastic refers to a specific type of molecule that is made up of polymers. Plastics are all human-made, and they come from oil or petroleum base, whereas polymers are also widely found in nature. There are two different types of plastic. There's thermosetting, which can be shaped only once, and there's thermoplastic, which could be reheated and reformed numerous times. This demo is on the process of polymerization. Let's say that these paper clips are all just the monomer isoprene. So polymerization is simply when the monomers connect to each other to form a long chain. So you take the monomer, in this case isoprene, and we connect them into a chain, and now we have polyisoprene. Poly meaning many. So there we have our long chain molecule of the polymer isoprene, or polyisoprene. And here we just start forming a second long chain molecule. So we've got two separate, they don't have to be the same length. They can be whatever length they form to, though they do tend to form to the same, because they're forming under the same conditions, they do tend to form similar chain lengths. So all we do is just connect them to each other, and we've polymerized our isoprene into polyisoprene. What happens when those polymer chains connect to each other is called crosslinking. What happens is that a catalyst, sometimes just heat, will be introduced, which will cause the backbone of the polymer to hold their bonds a little bit more loosely. That allows them to also form another bond outside of the polymer molecule. In that way, they can connect to each other. It happens randomly along the chain, not really in a set pattern, and it causes sort of a messy tangle of a molecule. A highly cross-linked molecule means that there's a relatively large number of those connections between the chain molecules. The more cross-linked it is, the stronger and more chemically resistant that molecule is. It also means that it's less elastic and less flexible. So now we're going to talk about cross-linking. We're going to start with those polyisoprene molecules that we made earlier. And as you can see, because they're just long chains, they're flexible, they can move around, they stay connected to each other, but they don't really have much limiting them beyond that. What happens is when we introduce our cross-linking agent, in this case sulfur, it connects to one chain and then it connects it to another. So now our molecules can't really move as freely because they're connected to each other, so they become a little more rigid. As our reaction goes on, and we cross-link in more and more locations, our polymers become even less flexible. They become locked to each other. They can even lock back to themselves. Make sure we get this one in there. So by cross-linking polymers, we change their properties. We make them less flexible and more rigid, because now they're more locked into the shape that they've created. One common example of a cross-linked polymer is vulcanized rubber. Natural rubber is a polymer that comes from tree sap and is made up of the monomer isoprene. It is very soft and easily melts and gets sticky. By introducing sulfur and heat, however, the polyisoprene chains become joined and leads to a much more useful product. So the carbons connect to these sulfur molecules, which are connected to each other, and it forms more of a grid than a chain. Vulcanized rubber is sturdy enough to be used in car tires without breaking down from the heat of friction or from the motor oil that it may encounter along the road. As I mentioned earlier, many polymers are naturally occurring. They're polymers in your food. Starches, sugars, and protein are all examples of polymers. Animal fibers, too, can be made of polymers, such as silk and wool. Plants and trees also produce naturally occurring polymers in latex, pectin, and rubber. This demonstration is going to be on cross-linking polymers. So we're going to start with our polymer, which is just regular school glue. And I watered it down to make it a little more watery, sort of make the reaction a little more impressive when we get to that point. And our cross-linking agent, which is just borax. So the borax I made into a supersaturated solution, meaning I just heated up the water so that more of the powder would dissolve in it. We're going to start with our polymer. Which is the glue. I'm going to pour it on the table because it looks cooler that way. So as you can see, it's just really liquidy here. And as soon as I start adding the cross-linking agent, those polymer chains are going to start connecting to each other across chains, which will make it more a rigid molecule. So you can see as soon as I pour it on there that something is happening. And when I start mixing it and rolling it together, you can see that it's combined to make like a slime. So those polymer molecules are cross-linked, making it more rigid and less flexible. Because this reaction is happening in water, because I've added water to both of them, the more I play with it, the more it dries out and the more highly cross-linked it becomes. As we talked about earlier, when you get a more highly cross-linked polymer, it gets even more rigid and more brittle and less flexible. So here it's still pretty flexible, pretty stretchy, gooey. And then as it starts to dry out, it'll start to get harder, more solid, less flexible.
to the point where once it gets kind of dry, there we go, I should even be able to rip it and break it, because this highly cross-linked polymer is brittle and less flexible.
Another variation of polymers is copolymers. These are ones that contain more than one type of monomer. So instead of being one long chain of the same monomer over and over, there are different monomers combined together in different combinations. This is helpful because then the polymer will get some properties from each of the monomers. By changing the ratios, how much of one monomer versus how much of the other monomer is in there, you can get different polymers made out of the same components in different combinations. The problem with copolymers is that they're more difficult to recycle because it's hard to separate them back down into their component monomers. Mostly, the only recycling of copolymers that's done is a manufacturing waste that can be put directly back into the original feedstock. One common type of copolymer is acrylonitrile butadiene styrene, usually heard to be called just ABS. What this is these three different monomers, acrylonitrile, butadiene, and styrene, mixed together to make this new product. Acrylonitrile gives chemical resistance, butadiene is flexible but it's not very strong, and styrene is strong but it's very brittle, so it breaks easily. When you combine these three different monomers together to make the polymer, ABS, you get their disparate properties all joined together, and that's what Legos are made of. That's how we get Legos that don't warp and fade over time.
This demonstration is about how copolymers are formed. So instead of starting with one monomer, like we did with our polyisoprene, we're going to start with three different types of monomer. So for this one, we're going to start with acrylonitrile, butadiene, and styrene. And when we form a polymer from these three different monomers, we end up with the copolymer that is often just called ABS. So when you form a copolymer, you end up with a new polymer that has some properties of each of the original components. In this instance, we just end up with different colors, but in reality, you'd also end up with different physical properties and chemical properties as well. If we formed a polymer with just the acrylonitrile, it would all be blue. If we formed a polymer with just the butadiene, it would all be green. And if we formed a polymer with just the styrene, it would all be yellow. But by combining the three of them, we get something different that has all of the properties, in this case color, mixed together.
The final variation of polymers I'm going to talk to you about today is functional groups. So as you've seen in all these molecular diagrams that I've shown, when the monomers bond to each other, they bond through their carbon atoms, carbon to carbon to carbon, making a long chain of carbons. That's called the molecule's backbone. The atoms that hang off of that backbone are what controls the properties of the polymer and make it act differently from other polymers. Those are called functional groups because they control the function. Another way of changing the properties of a polymer is to swap out the atoms that hang along the backbone and change its functional groups. How much difference can the functional group make? Well, here's an example. Hanging along this backbone of carbon is hydrogen atoms. That makes polyethylene. That gives us the plastic we use for our plastic grocery bags. If you swap out the hydrogens for fluorines, then what you get is polytetrafluoroethylene, and that gives us Teflon. So just by changing the hydrogens for fluorines, that makes the difference between plastic grocery bags and a Teflon. Okay, so what does that mean for you as designers? From this overview, I hope that you've learned that polymers can have many different properties and that they can have many different uses because of those properties. Also, if you're concerned about sustainability, polymers do come from many different sources, including natural sources. What I want you to take away from this is that you shouldn't limit your searches for materials. Because of cross-linking and copolymers, the polymers that you're considering using might have drastically different properties than you expect. Be sure that you do a thorough dive into any materials you plan on using in your designs. As with anything else, feel free to reach out to me. I'm at the Color and Materials Library, which is in the Taubman Center on 925. You can email me, you can call the library. We also have GChat. Or you can look for more information on the library's website, which is libguides.collegeforcreativestudies.edu. By going there, you can find links to our chat service, make an appointment for in-person browsing, or make a Zoom meeting request for a reference session. Thank you.